Today, we are talking about steel design and the kind of invisible philosophy that literally keeps our entire modern world from falling down around us.
I mean, have you ever really stopped and looked up at a giant skyscraper or driven over some massive bridge and just wondered how is that thing still standing? It honestly feels like it should be impossible. But it's not magic.
And the secret, it isn't just that steel is strong. Nope. The real reason is this really smart, really important engineering philosophy. Basically, a set of rules designed to stop failure before it even gets a chance to start. So what is this big secret? Well, it's a principle that guides pretty much all of modern structural engineering. It's called the limit state design philosophy. You can think of it as the #1 role for engineers. Its entire job is to make sure a structure is safe and does what it's supposed to do, not just on the day it's built, but for its whole life. And here's the thing, this isn't just for steel. This exact same way of thinking applies whether you're building with concrete or even with timber. It is the universal language of making sure things don't fall down. So how does this whole philosophy actually work? Well, it all comes down to a really simple and honestly a pretty clever balancing act. I want you to picture a scale. On one side, you have resistance. That's the structure's capacity, how much force it can possibly take. On the other side, you have the load. That's the demand, all the force we're actually putting on it. Now, to make sure it's always safe, engineers rig the game. They intentionally, on paper, pretend the resistance is lower than it is, and they pretend the load is higher than it's ever going to be. And that is the whole point. That's the entire game right there. The math has to show that the resistance side of that scale always wins, no matter what. It's the one rule that can never, ever be broken. So let's look at how they do that. First, engineers apply something called a resistance factor. It's basically a number less than 1 that they multiply the material's strength by. Why? Because they know that in the real world, nothing's perfect. There might be a tiny invisible flaw in the steel, and this factor accounts for that. Okay, so that's one side of the scale tipped. Then they go and tip the other one. They apply a load factor. They calculate all the forces they expect, from the building's own weight to people to snow, and then they artificially inflate those numbers. This covers all the what ifs. What if there's a record-breaking blizzard or a huge crowd gathers in one spot? They've already planned for it. Okay, so we know we have to reduce the material's strength on paper, but hang on. How do we even figure out what its true strength is in the first place? Well, the answer is in this incredible diagnostic tool called the stress-strain curve. It's really cool. Engineers take a piece of steel, they stick it in a machine, and they just pull it until it breaks, mapping out exactly how it behaves the whole time. And that curve, it tells the entire life story of that piece of steel. First, it enters the elastic region, where it stretches like a rubber band and would spring right back if you let go. But if you keep pulling, it hits the yield point. That's the point of no return, where the damage is permanent. But then, and this is wild, it actually gets stronger for a bit, in a phase called strain hardening. Then it hits its absolute peak, its ultimate strength, before it finally gives up and fractures. Engineers need to know every single one of those points. So you have all this super detailed knowledge about how steel behaves under pressure. How do you turn that into a practical formula you can actually use for safety? Okay, so at its most basic level, the tensile resistance, or how much you can pull on a steel bar before it yields, is just its cross-sectional area times its yield strength. Seems pretty simple, right? But remember, this is just the theoretical number. We haven't applied our philosophy of safety yet. So first things first, we apply that resistance factor. For steel, when we're checking for this kind of yielding, the engineering code says we have to use a factor of 0.9. That means engineers are only allowed to trust 90% of the steel's calculated strength. That other 10%, that's our safety cushion. But, the real world is messy. You can't just have perfect, solid bars of steel. You have to connect them somehow, and that usually means drilling holes for bolts. And, well, every single hole you drill creates a potential weak spot. So, to deal with this, engineers calculate something called the net section area. It's exactly what it sounds like. They take the total area and they subtract the area of the holes. They have to do a whole separate check to make sure the steel won't just suddenly snap right at that weaker spot. And because a sudden fracture, a snap, is way, way more dangerous than a slow, gradual yielding, the safety factor is even stricter. For this fracture check, engineers use a resistance factor of 0.85, and they apply it to the steel's ultimate strength, not its yield strength. This builds in an even bigger margin of safety right where it's needed most. So let's put this all together. What does this whole two-pronged approach, weakening the material and strengthening the loads, actually look like in the end?
This right here is the whole philosophy in a nutshell. On one side of the equation, the resistance side, we're deliberately reducing the strength we think we have to cover ourselves against any material flaws or the risk of a sudden fracture. On the other side, the load side, we're amplifying all the forces we expected to face to cover for any uncertainties or overloads the real world might throw at it. You know, when you really boil it down, this entire philosophy is a form of planned pessimism. It's brilliant, right? Engineers start with the assumption that the materials are a little bit weaker than they look, and the forces of nature are a little bit stronger than they seem.
So let's just quickly recap the big ideas. Real structural safety is a guarantee, not a guess. It's a formula, where the nerfed version of a structure's strength is still greater than the buffed-up version of the loads. We figure out a material's true limits with tools like the stress-strain curve, and then we build in these safety factors to protect us from the unknown. And remember, this powerful idea of planned pessimism is the invisible foundation holding up just about every major structure around you. So the next time you walk into a skyscraper or drive across a bridge, just take a second. You're not just standing on steel and concrete, you're standing on a philosophy, a kind of deep, careful pessimism that lets the rest of us live with a whole lot of optimism. Pretty cool, huh?